In this lecture, the ways in which geographic information systems are used in ecological planning processes and how they support informed decision-making are explored. Rather than functioning only as a mapping tool, GIS is addressed as an integrated decision support system that enables the analysis, interpretation, and visualization of spatial data. Throughout this presentation, the manner in which GIS brings together different types of environmental information and transforms them into meaningful inputs for planning is examined. First, the role of GIS within the planning process is discussed. Then, the main analytical tools used in ecological planning, such as spatial queries, proximity and overlay analyses, and other core spatial techniques, are explored. This presentation covers the fundamental concepts and applications of geographic information systems, GIS, in planning. It begins with the learning objectives and the definition of GIS, followed by an examination of the role of GIS in the planning process. Data sources are then introduced, with a particular focus on remote sensing, and remote sensing-based analyses are explained. Core spatial analysis techniques are discussed, demonstrating how spatial analyses are translated into planning decisions. Finally, the importance of GIS in planning processes is emphasized, and the presentation concludes with a summary of the key points. The learning outcomes of this course are as follows: to define geographic information systems, GIS, not merely as tools for map production but as integrated decision support systems within planning processes, to identify and explain the core spatial analysis methods used in ecological planning, including query, proximity, overlay, density, and network analysis, and to evaluate alternative planning scenarios by interpreting GIS-based analytical results in order to support evidence-based, sustainable, and resilience-oriented planning decisions. Geographic information systems, GIS, are integrated information and decision support systems that enable the collection, storage, analysis, and visualization of spatial data related to the Earth's surface. GIS goes beyond simple map production. It allows the integration of environmental, physical, and socio-economic data to support spatial analysis and informed decision-making processes. Through GIS, spatial data can be analyzed using various techniques such as query, overlay, proximity, and network analysis. These tools help reveal spatial relationships, patterns, and interactions that are essential for understanding complex environmental and urban systems. In this sense, GIS functions not only as a mapping tool but as a powerful analytical framework that supports data-driven and sustainable planning decisions. This slide illustrates the role of GIS in the planning process. GIS does not merely serve as a tool for producing data, it enables the analysis, interpretation, and integration of information to support decision-making. In this process, spatial data are first collected and then analyzed to generate meaningful insights. Through these analyses, environmental conditions, spatial relationships, and potential risks can be clearly identified. The results support the evaluation of alternative planning options and contribute to more informed and effective decision-making. In this way, GIS functions not only as a technical tool but as a core component of the planning process itself. Within the context of ecological planning, this decision support role of GIS enables the prioritization of nature-based solutions, thereby strengthening the adaptive capacity of urban and environmental systems and contributing to resilience. GIS uses a wide range of data sources obtained through different methods and technologies, rather than relying on a single source. These data sources include remote sensing data, digital and thematic maps, topographic and environmental datasets, socio-economic and demographic data, institutional and open-source databases, field-collected data, and GIS-derived analytical outputs. Among these sources, remote sensing stands out as one of the primary data sources used in GIS. Satellite imagery and aerial photographs enable continuous monitoring of the Earth's surface, allowing land use patterns, vegetation cover, and environmental changes to be observed over time. In addition to remote sensing, field surveys, sensor-based measurements, and statistical data provide important inputs for spatial analysis. All of these data sources are integrated within a GIS environment, where they are analyzed and transformed into meaningful information for planning processes. In this context, key data types derived from remote sensing include land use and land cover, LULC, vegetation indices such as NDVI, land surface temperature, LST, water distribution indicators such as NDWI, and topographic data derived from digital elevation models, DEM. These datasets play a critical role in assessing environmental conditions, identifying spatial patterns, and supporting informed decision-making in ecological planning. In this slide, focus on remote sensing-based analyses. Remote sensing is one of the primary data sources in spatial analysis, enabling the collection of information about the Earth's surface through satellite and aerial imagery. One of the most commonly used analyses in this context is land use, land cover, LULC, analysis. Land cover refers to the physical characteristics of the Earth's surface, such as forests, water bodies, agricultural land, or bare soil. Land use, on the other hand, describes how humans utilize these areas, including residential, industrial, agricultural, or recreational purposes. When considered together, land use and land cover data provide critical insights into both natural conditions and human activities. LULC analysis plays a key role in identifying environmental changes, monitoring land transformation processes, and supporting sustainable planning decisions. In this slide, focus on remote sensing-based analyses, particularly two key indicators, NDVI and NDWI. First, NDVI, Normalized Difference Vegetation Index, is used to assess vegetation density, health, and vitality. It provides valuable information about the distribution of green areas and the condition of vegetation cover. NDVI is widely used to evaluate ecosystem health, monitor vegetation changes, and support sustainable land management practices. On the other hand, NDWI, Normalized Difference Water Index, is used to identify surface water bodies and moisture conditions. It helps detect water bodies such as rivers, lakes, wetlands, and temporary water accumulations. NDWI is especially important for analyzing flood-prone areas, water availability, and wetland dynamics. When used together, NDVI and NDWI enable a comprehensive understanding of both vegetation and water systems, supporting integrated environmental assessment and informed spatial planning decisions. In this slide, focus on remote sensing-based analyses, particularly land surface temperature, LST, and topography derived from digital elevation models, DEM. First, land surface temperature, LST, is used to identify temperature variations across the land surface. It helps us understand where heat accumulates and how thermal patterns differ across urban and natural environments. LST analysis is especially important for detecting urban heat islands, assessing thermal stress, and supporting climate adaptation strategies in urban planning. On the other hand, digital elevation models, DEM, provide detailed information about the elevation and shape of the terrain. Through DEM data, we can analyze slope, elevation, and terrain structure, which are critical for understanding drainage patterns, flood risk, erosion processes, and land suitability. These analyses enable the spatial interpretation of different environmental processes within the scope of ecological planning, allowing heat-sensitive areas and topographic constraints to be incorporated into planning decisions. Spatial analysis constitutes one of the fundamental functions of GIS in planning and environmental assessment processes. These analyses focus on understanding, interpreting, and visualizing spatial relationships among geographic data. They address not only the question of what is located where, but also more complex planning questions such as why is it located there, how are spatial elements related to one another, and what spatial patterns emerge. Spatial analyses conducted within a GIS environment reveal interactions among datasets, enabling the identification of patterns, concentrations, thresholds, and processes. In this way, environmental risks, sensitive areas, potentials, and spatial conflicts can be evaluated analytically. Particularly in planning and environmental impact assessment studies, these analyses provide a scientific basis for decision-making processes. Although GIS includes a wide range of analytical methods, certain spatial analysis types are more commonly applied in planning practice. These analyses play a critical role in supporting land use decisions, conducting environmental suitability assessments, performing risk analyses, and developing sustainable spatial strategies. Spatial analyses form the analytical foundation of resilience-oriented planning by enabling the assessment of risks, vulnerabilities, and adaptive capacities. In this slide, we focus on query analysis. Query analysis is a fundamental GIS method used to select and extract spatial features based on specific criteria. It allows users to identify relevant information from large spatial datasets in a systematic way. Query analysis can be divided into two main types: attribute-based queries and spatial queries. Attribute-based queries select features based on their attribute values, such as identifying areas with a population above a certain threshold or areas with slope values exceeding a defined limit. Spatial queries, on the other hand, are based on spatial relationships between geographic features. These include questions such as whether one feature contains another, whether two features intersect, or which features are located within a certain distance. Spatial querying is one of the fundamental functions of GIS because it enables the clear identification of spatial relationships such as proximity, overlap, and interaction in planning processes. It allows the comparison of alternative areas to support informed decision-making. It facilitates the visualization of analysis results, making interpretation easier and more effective. It provides objective and repeatable outcomes for planning, environmental assessment, and risk analysis processes. In this slide, proximity analysis is discussed. Proximity analysis is a type of GIS analysis based on measuring the distance between one feature and other surrounding features. It helps identify spatial relationships between points, lines, or areas. The most commonly used method in proximity analysis is buffer analysis. Buffer analysis defines a specific distance around a geographic feature to represent its area of influence. Through this method, it becomes possible to identify which areas fall within the influence of a given feature and to what extent they are affected. Proximity analysis is widely used in planning, transportation, environmental assessment, and risk analysis processes. Overlay is one of the core analytical techniques within GIS. It enables different spatial data layers, such as land use, topography, vegetation, hydrology, or protected areas, to be superimposed and analyzed simultaneously within the same spatial framework. Through overlay analysis, GIS reveals spatial relationships, overlaps, and intersections between layers, allowing planners to understand how multiple environmental factors interact within a given area. This technique is particularly valuable for suitability and constraint analysis, where areas appropriate for development, conservation, or risk mitigation can be identified based on combined environmental criteria. As a result, overlay analysis supports more systematic, evidence-based, and environmentally responsible planning decisions. In this slide, density analysis is presented. Density analysis is a fundamental spatial analysis method used to identify how intensively a phenomenon is distributed across a given area. It helps reveal the concentration of features by calculating their density within a defined space. This type of analysis is widely used to examine population density, building concentration, traffic intensity, and environmental pressures. It enables planners to identify areas of high concentration as well as zones with lower levels of activity or development. Furthermore, density analysis plays an important role in evaluating urban growth patterns, identifying risk-prone areas, and supporting infrastructure planning. For these reasons, it is considered a key analytical tool in spatial planning and environmental assessment processes. This slide focuses on network and connectivity analysis. This type of analysis is used to examine connections, accessibility, and movement patterns within spatial networks. Network analysis helps us understand how people, vehicles, or services move through transportation networks, infrastructure systems, and service networks. Through this analysis, it is possible to identify the shortest or most efficient routes, evaluate accessibility levels, and define service areas. In addition, network analysis allows the identification of bottlenecks, disconnections, and accessibility issues within urban systems. For this reason, it plays a crucial role in transportation planning, emergency management, public service distribution, and sustainable urban planning. In planning processes, decisions are often guided by questions such as where, how much, and which areas should be prioritized. Geographic Information Systems, GIS, transform these questions into measurable and analyzable components that support informed decision-making. Using data derived from remote sensing and other spatial sources, planners can analyze variables such as land use and land cover, topography, population distribution, accessibility, and environmental risk. Through spatial analysis techniques, these datasets are evaluated to answer key planning questions such as, where should new green spaces be located? Which areas should restrict development due to flood risk? Which zones are most suitable for future urban growth? To address these questions, different analytical approaches are applied. Query analysis identifies where specific conditions occur. Proximity analysis evaluates spatial relationships and distances. Overlay analysis examines how multiple spatial factors interact. Density analysis reveals areas of concentration or intensity, and network analysis assesses accessibility and connectivity within urban systems. Together, these analytical methods enable planners to transform spatial data into meaningful insights, supporting evidence-based, sustainable, and resilient planning decisions. Up to this point, we have examined how spatial analyses are used within the planning process and how different analytical methods contribute to decision-making. At this stage, it becomes important to understand how these analyses are transformed into actual planning decisions. This leads us to the relationship between spatial analysis and decision-making. From spatial analysis to planning decisions. At this stage, we focus on how spatial analyses are translated into planning decisions. GIS does not merely visualize data, it transforms analytical results into meaningful inputs that support decision-making processes. Through spatial analysis, raw data is evaluated, compared, and interpreted to support informed planning choices. These analyses help identify which areas should be protected, where development should be encouraged, and where intervention may be required. In this context, spatial analysis provides the foundation for evidence-based planning by enabling planners to assess alternatives, evaluate impacts, and prioritize actions. As a result, GIS functions not only as a technical tool, but as an integrated decision support system that guides the transition from analysis to planning action. These analyses help transform data into concrete planning decisions. GIS makes it possible to compare different scenarios and identify the most suitable planning options. In planning processes, decisions are not based on a single predetermined option, instead, they are shaped through the evaluation of multiple alternatives. Geographic Information Systems, GIS, support this process by transforming planning into a dynamic and iterative decision-making framework. Through GIS, different planning scenarios can be developed, alternative land use options can be compared, various density levels, development patterns, or conservation strategies can be tested, the spatial impacts of infrastructure and transportation decisions can be evaluated. In this way, GIS enables planners to move beyond single-solution approaches and make informed, sustainable decisions by comparing and assessing multiple scenarios. In this stage, GIS plays a key role in supporting planning decisions by transforming analytical results into actionable insights. Suitability maps help identify areas that are appropriate for specific land uses, such as development, conservation, or infrastructure, based on defined spatial criteria. Through prioritization and intervention sequencing, planners can determine which areas require immediate attention. By evaluating risk, vulnerability, and exposure, GIS supports informed decisions about where investments, mitigation measures, or redevelopment efforts should be focused. Additionally, spatial analyses related to hazards, such as flooding, landslides, or urban heat islands, contribute to risk reduction and resilience-oriented planning. In this way, GIS supports not only effective spatial organization but also long-term, sustainable, and resilient urban development. The importance of GIS in planning. GIS-based analyses go beyond merely describing existing spatial conditions. They enable a deeper understanding of how cities evolve over time, the dynamics that shape urban transformation, and how future changes can be managed more effectively. In this sense, GIS transforms planning from a static exercise into a dynamic process that integrates spatial and temporal dimensions. By integrating diverse spatial datasets, such as land use and land cover, population distribution, environmental conditions, topography, and infrastructure networks, within a GIS environment, planning decisions can be evaluated in a comprehensive and multi-dimensional manner. This integration makes it possible not only to identify areas suitable for development, but also to delineate ecologically sensitive zones, environmental thresholds, and areas vulnerable to disaster-related risks. GIS-based spatial analyses allow planners to compare alternative planning scenarios and to assess their potential environmental, spatial, and social impacts prior to implementation. Rather than producing a single predetermined solution, this approach supports informed choices among multiple alternatives. In the context of increasing uncertainty, climate change, and disaster risks, scenario-based evaluation has become a fundamental component of contemporary planning practice. Within this framework, GIS moves beyond its role as a tool for data visualization and supports planning approaches that prioritize sustainability, risk reduction, and adaptive capacity. By enabling the identification of nature-based solutions, strengthening ecological systems, and reducing spatial vulnerabilities, GIS-based planning processes directly contribute to enhancing urban and environmental resilience. Ultimately, GIS plays a central role in guiding evidence-based, adaptive, and resilient planning decisions. Throughout this presentation, the critical role of geographic information systems, GIS, in ecological planning processes has been demonstrated. It has been shown that GIS is not merely a tool for map production, but a powerful decision support system that actively guides planning decisions. The use of GIS enables planning processes to move beyond intuition-based approaches and supports the development of evidence-based, data-driven, and sustainable decisions. By analyzing multiple spatial datasets simultaneously, planning becomes more transparent, consistent, and scientifically grounded. By prioritizing nature-based solutions, ecological planning inherently provides a framework for urban, environmental, and societal resilience. In conclusion, the integration of GIS into ecological planning strengthens the capacity to develop more sustainable, resilient, and informed spatial strategies for the future.